We present MuSCLE, multi-sweep compression of LiDAR using deep entropy models. LiDAR sensors play a key role in robotics applications, thanks to their ability to capture 3D geometry and appearance. A major challenge with LiDAR data is its memory footprint. These sensors can produce over 3 billion points per hour, resulting in over a terabyte of data per day. As a result, compression of vast LiDAR data becomes crucial for these robotics applications to become more accessible. We make key insights that we can model both sparse spatial structure and temporal redundancy of LiDAR point cloud sweeps using a deep neural nets. From these motivations, we present MuSCLE, a novel compression algorithm exploiting spatial temporal relationships across multiple LiDAR sweeps to reduce the bitrate of both geometry and intensity values. Prior works have utilized various methods, like range images or voxelizations, for storing point clouds. We use a memory-efficient octree-based approach, which allows us to control reconstruction quality by altering octree depth. Recent work of octrees focuses on LiDAR geometry in a single-frame setting. We extend on this by utilizing temporal context between frames to further compress LiDAR geometry and additionally compress LiDAR intensity. We now present our joint method. First, we quantize our input point clouds by storing them in octree structures. Next, we perform geometric encoding to build an entropy model of the nodes of the current sweep's octree. The goal of entropy encoding is to accurately predict the probability of each 8-bit node occupancy symbol. The more accurate these predicted probabilities are to the actual distribution, the further we can compress our bit stream. Since we traverse octree nodes in breadth-first order, we first do top-down feature aggregation in our current sweep to aggregate context from ancestor nodes. For the past sweep, we use both top-down and bottom-up aggregations to construct temporal context per node. We then use continuous convolution to aggregate these temporal features from the past to our current octree. Continuous convolutions are learned convolution layers for non-grid structured data, making it well suited for LiDAR. Finally, we use the resulting probabilities for entropy encoding to get a geometry bit stream. Similarly, we also perform entropy encoding for our intensity bit stream. Similar to a geometry model, we predict the probability of each 8-bit LiDAR intensity symbol for every reconstructed geometric point. We use continuous convolutions on the points in the previous sweep and use the resulting probabilities to get our intensity bit stream. Our method allows us to improve LiDAR compression 15 to 35%. Here's some qualitative results. First, we vary reconstruction quality by altering octree depth. We also show downstream object detection. Our method allows similar mean average precision while massively reducing bitrate. Similarly, we show downstream results on semantic segmentation. Our method achieves similar mean IOU while reducing bitrate significantly.